When measuring quantities, it can be either a static measurement or a dynamic measurement. A static measurement is when we measure a quantity that does not change with time. For example, if we're measuring beam deflection under a constant load, that beam deflection would be a static value. Dynamic measurements, on the other hand, are whenever we measure a time-varying quantity. Imagine if that beam is set into vibration, then the displacement measurement would be a dynamic measurement. In this video, we're going to look at characteristics of dynamic systems, and this is going to be a lot of review from differential equations. Here is the differential equation for a system where our system variable is x. The order of the system is given by the highest number of derivative that we have for x with respect to time. So here we have an nth order differential equation. And on the right hand side we have the forcing function, f of t. Typical forcing functions are the step function, where it's just a constant value, or a sinusoidal forcing function. We're going to look at now three different order systems. Here's the equation for a zeroth order system. In this system, the response, or the system variable x, follows the forcing function with no delay. There is just some scaling factor, 1 over a0, and that's the sensitivity of our system. Then a first order system, the equation looks like this, and dividing through by a0 we get this equation. And the term a1 over a0 is the time constant. So we're going to look at first order systems in more detail later, and we'll see the significance of the time constant. Now second order system, here's the differential equation. And dividing through by a2 and substituting terms, we get this form where we have the coefficient for the first order derivative is 2 times zeta times omega n, and then omega n squared is the coefficient for the zeroth order term. And omega n is the natural frequency for this system. It's defined as the square root of a0 over a2. The damping ratio is a1 over the critical damping coefficient c sub c. And this we'll look at in more detail later also, the damping ratio that is. Examples of these systems in measurement are as follows. So maybe for the zeroth order system, if we think of we're measuring the displacement of, say, a slinky, and we put a ruler right next to the slinky, well then if x is our system variable, that would be the measurement that we see on the ruler, and so that would follow along exactly at the same rate that the slinky changes. Might not be the clearest example, but there's no lag. There's no the measurement doesn't lag at all behind the forcing function, which would be the displacement of the slinky. Okay, first order example. Our system variable x could be the temperature readout on a glass bulb thermometer, and the forcing function, say it's a step function where we put that thermometer into a glass of hot water. Now the temperature readout is not going to instantaneously change from room temperature up to the temperature of the water. Instead, it's going to change according to this first order differential equation. And then a second order system, you could think of a scale, maybe a bouncy scale. If you step on a scale, then the needle might shake back and forth for a little bit before it settles down at your true weight. More detail on the first order systems. Here is the differential equation again. And for these differential equations, we're going to say that the time response is the sum of a homogeneous solution and a particular solution, x sub h and x sub p. And that's because these are linear differential equations. Our equation for the homogeneous solution is going to be c times e, or the exponential of b times t. And here's the derivative of that. So substituting the homogeneous solution, its derivative, into the homogeneous equation, we get this equation. And we can divide through by c times e to the bt to get this, and that gives us a value for b. So bringing that back up here to the homogeneous solution, we have c times e to the negative a0 over a1 times t. And if you remember from the previous slide, a0 over a1 was the time constant, and we're going to call that tau. So here is the homogeneous solution, c exponential negative t over tau. Let's look at the step response for a first order system. The forcing function is a constant a, and we're going to assume that the particular solution is another constant value. We'll call it d. The derivative of the particular solution is 0. So if we substitute the particular solution into the differential equation, then we get this line. And we can find out what our value for d is. So the particular solution is the amplitude of the step input divided by A0. Now we're going to substitute the particular solution here and the homogeneous solution into our solution for x. So the time response x of t is c to the e to the negative t over tau plus a over a0. And we use the initial condition, the time response at time 0 is x sub 0, and substitute that into this equation in order to find the value for c. X sub 0 is c, and then our value for t is 0. And rearrange that to get c is this value, x0 minus a over a0. Bringing that back up here into our time response equation, we get this equation. And the steady state value, so x at time infinity, we can find that by substituting infinity in for t. It's a over a0, and we'll call that x sub infinity, or the steady state response. So we can substitute that into this equation, and here is our time response for the first order system for a step input. So we have initial value minus the steady state value times this exponential t over tau plus the steady state value. And we can rearrange this equation to look at some of the characteristics of a first order system in a step response. Here's that rearranged time response equation again. Let's see what is the response of the system at one time constant. So we'll substitute tau for t, and we end up with this. So this ratio is the difference between the time response and the steady state value divided by the difference between the initial value and the steady state value at t equals tau is equal to the e to the negative 1, which is 0.37. Rearranging that, we get that the time response at one time constant is this, and then we can expand that, regroup terms, add and subtract x0, and then we get that the time constant has, at one time constant, our response has reached 63% of the change from initial to final value. So at one time constant, our response is going to be the initial value plus 63% of the difference between the initial and steady state values. Rise time we define as the time that it takes for the response to change, or to exhibit 90% of the change from initial to final values. By definition, that's what's given in this equation. The time response at rise time is going to be the initial value plus 90% of the difference between initial and steady state values. So we can put that into this equation, x of t, and substitute t sub r for the time. And we can rearrange this as follows. And so we end up with 0.1 is equal to the exponential of negative rise time over time constant. And we end up with the rise time being 2.3 time constants. So for a step input for a first order system, after 2.3 time constants, the output or the system variable is going to be 90% of the way to its steady state value. Now we will look at second order systems for the rest of the video. Here's the differential equation, and again the solution is going to be the sum of a homogeneous solution and a particular solution. Homogeneous solution takes the same form. We assume the same form, c times exponential b times t. Here's the derivative of that and the second derivative. And now substituting these three terms into the homogeneous solution, where the forcing function is 0, homogeneous equation, where the forcing function is 0, we get this. And again, we can eliminate terms to end up with this expression. And we can solve that for b. So now we have the term b here in this equation. And you can see that this can have different values. This could be a real value. It could be imaginary, complex conjugates, and we're going to look at all those in more detail. So, first case, if this term is equal to this term, then the difference under the square root is going to be 0. So we'll have negative a1 plus or minus 0 divided by 2a2. And that is the case where, if we go back to the definition of the damping ratio is 1. That's what's called a critically damped system. And in that case, we have roots of negative a1 over 2a2. So we have repeated real roots to the characteristic equation. And what we have to do for that solution is we'd end up with c1 times e exponential the first root times t, and then in order to have a second independent solution, that would be c2 times t times e to that same exponential. And the response here is that it exponentially approaches a steady state value. If we have this term, the term under the square root is positive, a1 squared is greater than 4a2a0, then we have two distinct real roots. So we have b1 and b2, and they differ by, this one is, we're adding the term, the square root, and here we're subtracting the square root. And in that case, we end up with this expression for our homogeneous solution. We have c1 exponential b1t plus c2 exponential b2t. And again, this exponentially approaches the steady state value more slowly than the critically damped system. And the other case that we'll look at is if we have a1 squared less than 4a2a0. So in that case, we would have a negative value in the square root. So we'd have complex conjugates for b. Well, I guess there's a fourth case too, where we would have an undamped system. So zeta would be 0, and in that case, a1 is 0. So here we'd have no damping in the system. And that would just be an undamped system, so a spring and a mass, but no loss. Anyway, back to the underdamped system where we have imaginary roots to the characteristic equation. Here is b, and if we have a1 squared less than 4a2a0, then we can rewrite this like so. Expanding that, and then we get this, and then we'll substitute the expression for zeta. Zeta squared is this term, so we can substitute that into this expression. We end up with b is this in terms of zeta squared, a1, a0, and a2. And that we will rewrite as alpha plus or minus I times beta. So here we have b is alpha plus or minus I times beta, and we'll make those substitutions into this equation. So we're going to have two distinct values for b. So we have b1 and b2. So we have these two solutions for our homogeneous solution. And each one is going to have a constant coefficient, Ca and Cb. So here we'll make our substitutions for b1 and b2. We have alpha plus ib and alpha minus ib. And just rearranging that, we get this expression. And now we can substitute e to the I beta t. So that looks like this. And negative e to the negative I beta t looks like this. Rearranging this, we end up with such and such. And now we're going to say that Ca is a plus bi and Cb is a minus bi. So making those substitutions, we end up with this. And now we see that our homogeneous solution is C1 times e to the alpha t times cosine beta t plus C2 e to the alpha t sine beta t. And if we look back at the definitions of beta and alpha that we found here, beta is given by this quotient, and we can rearrange that and use the definition of the natural frequency. So we have the natural frequency times square root 1 minus zeta squared. And this term, beta, is known as the ringing frequency. And again, alpha is negative zeta times omega n. So the damping ratio times the natural frequency. And you can see those here. And that alpha term determines how quickly our homogeneous solution is going to decay, and beta determines the frequency at which the harmonics will oscillate. So we can make those substitutions into our homogeneous solution, and it looks like this. Now, just to review the total solutions for the three cases, overdamped, we have two distinct real roots. Critically damped, we have repeated real roots, so the solution takes this form. And underdamped, we have complex conjugate roots of the characteristic equation. In order to get C1 and C2 for all of these different solutions, we need two initial conditions for X. Now we're going to look at the step response for a second order system. And here's the differential equation. C is our forcing function, it's constant. Again, the total solution is going to be the sum of a homogeneous solution and a particular solution. Here the particular solution is just a constant, which is the steady state value. So one note about the homogeneous and particular solutions, they have other names. They can be called the transient response and the forced response. So the transient response is what we found here, and it's going to die out over time, but the forced response is what will persist after the transient response dies away, and so that would be the particular solution. Okay, back to the sinusoidal response. Here's the differential equation. The forcing function is sinusoidal, where we have C is the amplitude and omega 1 is the frequency. Now our total response is again going to be the sum of the homogeneous and particular solutions, and in this case the particular solution is another sinusoidal, and we have x sub 0 times cosine, and it's going to be oscillating at the same frequency as the forcing function, but it has some phase shift, and the amplitude will be different. So this, again, there will be some transient response from the homogeneous solution, and then the steady state response will be the particular solution. And that steady state response will have a different amplitude. It might have a different amplitude than the forcing function. It'll have the same frequency, but it might have a phase shift. Here is the second order step response for systems with different, second order systems with different damping ratios. You can see if the damping ratio is 0, so if it's an undamped system, then we will just end up with pure undamped oscillations around the steady state value. And then as the damping ratio increases, we end up with oscillations that die out over time. So the amplitude here is bigger than the amplitude here. And the higher the damping ratio is, the faster the transients die out. So the bigger the exponential, negative exponential term is, so it gets smaller more rapidly as time increases. And then you can see there are different responses for undamped, underdamped, which is what we just covered, critically damped, so if zeta equals 1, we see an exponential response. It approaches the steady state value, and overdamped. Again, we have an exponential approach to the steady state value, just at a slower rate than critically damped. Now the steady state response for a sinusoidal forcing function is shown in these two figures. Again, here's the steady state response. We have the amplitude x0. So this figure plots the amplitude ratio x0 over, here it says f0 over k. In our example, it would be c over a0. So you can see that for an undamped system, the amplitude is going to increase as the forcing function frequency gets closer to the natural frequency. So on the horizontal axis, we're plotting the forcing function frequency, omega 1, over the natural frequency, omega n. So for an undamped system, when the forcing function, when the omega 1 equals omega n, then we have an infinite amplitude for an undamped system. As we add damping, that amplitude decreases. And it's still greater than 1 for an underdamped systems. Now, one other thing that you can see for the underdamped systems is that the amplitude ratio is 1 all the way up until about 0.3 or 3/10 of the natural frequency. So for that range, for low frequencies, these underdamped systems have good sensitivity. The output amplitude changes at the same rate as the input amplitude. For the steady state response, there's also this phase shift, and that's shown in the second plot. And we can get the phase shift from this equation relating the phase shift to the damping ratio, the natural frequency, and the input frequency. And you can see that plotted here for different values of damping ratio. The reason we covered all this material is that whenever we're taking measurements of dynamic systems, we also need to take into account the dynamics of our transducer. For example, I talked about the thermometer. It is a first order system. Mechanical scale would be a second order system. And you can see here the response. The output is going to vary based on the input and the parameters for that measuring system or the transducer. This can result in distortion, where our output signal varies a lot from our input signal. In this plot, we have the true signal shown in the solid line, and it's a complex signal where we have lots of different frequencies making up this signal. And so for each of those frequencies, we're going to have a different phase shift and a different amplitude ratio. So here in this dashed line we see the phase shift distortion, and in this, phase shift distortion, and then here there's frequency distortion. So whenever we add up all these different frequencies in the input signal, and those frequencies are changing with time, then the output is also going to have phase shift and amplitude distortions that are going to be changing with time. And we will need to take into account the characteristics of our transducer dynamics in order to reproduce the true signal.